Now you could have 2p orbital, you could also have 3p orbital, but 2 and 3, the quantum number, the principal quantum number is different. So there's nothing wrong with that. But on the p level there, on the second level there, you can only have 3p levels, 3p operators there, and that's -1, +1, and 0. Okay? And you cannot have two identical numbers representing the same operator. So here we say each set contains one quantum number that is not allowed. So here, which quantum in A, which quantum number is not allowed? N equals to 3, L equals to 3, ML equals to +2. Well, you gotta remember the relationship. L has to be n-1. The maximum value for L is n-1. If n equals to 3, L cannot be 3. L is not allowed to be 3. Okay. This set, which one is not allowed?
-2.
-2 is not allowed, because when L equal to 1, it
-1.
can only be -1, 0, +1. You cannot have -2. And this one, n equals 1, L can only be 0 when n equals 1. This is not allowed. So this is the practice that we give you in the textbook there. Okay, and giving you a set of quantum number, you need to be able to identify whether that set of quantum number is allowed or not allowed, based on their relationship, based on the relationship among those three different quantum numbers there. Okay, so only circle that circle shouldn't be there. So here's another one. We were only talking about in the previous test there, example there. We're only talking about the first three quantum numbers. And here's another example involving all four quantum numbers. Which set is not allowed? Why?
E.
Why? MS can only have two possible values, either +1 of 2 or -1 of 2. Cannot be 0. Okay. So the idea here is that when you are given a set of quantum numbers, you need to determine whether it's allowed or not allowed, and that's what's important there. Every other set of quantum number that you see here, the first three quantum numbers, they're all allowed. Now, these set of quantum numbers are equivalent to the postal address for each of the electrons. Okay, so if you have an incorrect postal address, well, USPS will not deliver. So, well, they may not deliver more than the applications there, but the thing here is that you have, in order for them to deliver to you, and you have to have the correct address. They have to put on the envelope so they can do the delivery there. But this one is an incorrect postal address there. MS cannot be 0. MS can only be -1 of 2 or +1 of 2. Those are the only two possible values. Why is this important? Well, this is one of the fundamental things that we originated from the quantum theory there, and this is one of the fundamental things that how we distribute the electrons. Remember at the beginning of the first warning objective in chapter 1, I said, well, we need to be able to determine how the electrons are being distributed. And based on the quantum theory, we assign, actually, Schrodinger's equation, the first three set of quantum theory equations there. Those are three mathematical equations, and calculate n equals 1 to n, L, and ml values. And it actually determines the possible values for a given atom. We know how many electrons in there. Using the quantum mechanics theory there, we can actually determine how the electrons are being distributed. And that's important there. Okay, so we will look at the quantum number, and we will try to determine how the electrons are being distributed. And so this is something that after the introduction of the quantum theory there, and this is something that we want you to understand. So instead of getting you into the complex quantum theory there, as long as you remember the basic relationship among N, L, ML, MS, we're okay. There are many different practice questions assigned in chapter 7. So I want you to make sure that you take the time and work on the homework assigned in there. Now, the example that we gave you here is only a part of the things that we need you to be able to do. Once again, what I need you to remember or memorize, if you will, I'm going back to that particular table, the relationship among the first three quantum numbers. Okay, so for that, we wrap up chapter 7, and we'll take a short break, and we'll come back and we'll continue with chapter 8. And again, homework number 2 covers everything from chapter 4 through 8. We finished chapter 7 now, and I would expect you to finish working on all questions assigned in chapter 7 and start working on chapter 8 tonight. And the homework is not due tomorrow, rather the homework will be due next Monday. And we will try to finish chapter 8 either today or the latest by Thursday, and so that you have at least you have a weekend to study and work on the homework assignment in chapter 8. And then when we finish chapter 8, exam number 3 will cover everything from chapter 6, chapter 7, chapter 8. That's what the third exam is going to be about. So when you come back after the break, we will start chapter 8. All right, let's take a break, and we'll continue the discussion after the break. I know the quantum theory, the quantum numbers may be a bit overwhelming, but it's really not that complicated. So take your time and review the material.
I'm waiting.
Well, you know the molarity of the oxide gases. The molarity represents moles per liter. So if you take 1 liter of that solution, you have that many number of moles. You take 0.02 liter. The molarity liter cancels out. That will give you 8 moles. Yeah. Molarity is moles per liter, so that's our conversion factor. Oh, the water. The water is when you dissolve that solid in water. Water is mixed with water. So we're talking about just H2O. With H2O, no.
Yeah.
It's the same. No, it's the same thing. That just should be H2O. Many times.
I don't have to say that.
Well, the thing here is that technically speaking, we should put about 2 behind it. But